How you doing, Connor? It is the right stream. Just running a bit late today. Now we're ready to work. How are we doing? Questions? Consider this. Last time we introduced Rolle's theorem and the mean value theorem. Use those to prove some nice results, right? Namely that If the derivative is always 0, the function had to be constant. If two functions have the same derivative, they can only differ by a constant. Very nice results, very important. Especially important, as people suggested, for next semester, meaning, right, I mean, here we're taking a function and we're finding the derivative. Next semester in 141, you'll be taking a function and asking the question, what function gave rise to that one via differentiation? In other words, what is the antiderivative? And that question is going to make sense because of the mean value theorem, right? The antiderivative is unique to within a constant. Otherwise, we would have been in trouble. Consider this question. Verify that this function satisfies the hypotheses of Rolle's theorem on the interval -2 to 2, and find all C satisfying the conclusion. You may recall Rolle's theorem. Rolle's theorem asks that the function be continuous on a closed and bounded interval, and this being a polynomial, that is certainly continuous everywhere. So continuous on this closed and bounded interval. You need the function to be differentiable on the open interval. And again, being a polynomial, it's differentiable everywhere. How do you know when to use Rolle's versus mean value theorem? Well, here there's no question, right? It does say Rolle's, so there it is. But it's a valid question. Let's hold off on that and we'll see some examples. Right, in general, I hear you. And in general, you'll see that it's not so clear. Well, the Rolle's versus mean value is usually pretty clear because the Rolle's theorem has the added condition that your function needs to be equal at the endpoints versus the mean value theorem, which does not. And as we saw, Rolle's theorem is really a special case of mean value theorem. So you can never go wrong in applying the mean value theorem all the time. The better question, though, is how do you know to use the mean value theorem in a certain question? And that's never really easy to answer. We'll take a few examples to point that out. But this polynomial, very well behaved, continuous, differentiable everywhere, so certainly continuous on the closed and bounded interval and differentiable on the open interval. Last hypothesis of Rolle's theorem is that the function should be equal at the endpoints. So let's figure out f of -2. That's going to be -8 minus 8 plus 8 plus 2, so that is -6. And f of 2 is 8 minus 8 minus 8 plus 2, which is again -6. So f of -2 is equal to f of 2. Thank you, Pratik. They are both -6. So f of -2 is equal to f of 2, and now we are in a position to find the conclusion of Rolle's theorem, right? I mean, this function satisfies all the hypotheses of Rolle's theorem. So by Rolle's theorem, there exists a C in the open interval such that f prime of C is 0. What is f prime? F prime is 3x squared minus 4x minus 4. Does this factor nicely? Does this factor nicely? It does factor. 3x. Then x. What is it? Plus 2. No. Minus 2. Plus 2 like this. So minus 6 plus 2 is minus 4. There you go. There you go. Thank you, Eddie. And so you see that x is 2 or x is minus 2/3. And only one of these is in the interval, the open interval, right? This is not in the open interval. Rolle's theorem guarantees at least one value in the open interval. There could be more. In this case, there's only one, -2/3. Shall we do one more? Jake is asking, why is 2 not in the open interval? Well, the open interval does not include the endpoints, and 2 is an endpoint here. So 2 is not in this interval. Are Rolle's and the mean value theorem the same? They're not. They're not. Rolle's has this one added condition that f of a and f of b must be equal, whereas the mean value theorem does not have that condition. The conclusion of Rolle's is that the derivative has to be 0 somewhere, versus the conclusion of the mean value theorem is that the derivative has to have the same slope, or the tangent line has to have the same slope as the line joining the two endpoints of the graph. Right? We saw, or you should convince yourselves, that Rolle's is a special case of the mean value theorem. But we used Rolle's theorem to prove the mean value theorem. So they are equivalent. Thank you. This is not number 10, but rather number 18. Will the exam specify which theorem to use? It will not. It will not, because these two examples are too easy. Well, actually, no, they're not too easy. They're not too easy. They could be good final exam questions. In that case, you have to know what the mean value theorem actually says and know how to use it. So that they would have been good questions. There's still time to put it on. Interesting. So who knows? To answer Lauren's question, who knows? Maybe they will ask, maybe they will tell you, maybe they will not. Gabrielle is asking, in the big picture, what does it mean? Well, Rolle's theorem says that if you have a continuous and differentiable function that starts and ends at the same place, the derivative has to be 0 somewhere. This was Rolle's theorem. In the mean value theorem, says that the slope of the tangent line should be the same as the slope of the line joining the two endpoints of the graph somewhere. That's what it means. That's what they're saying. That's it. We saw some nice corollaries of the mean value theorem last time. Colin is saying mean value theorem says the slope connecting the two lines is the slope at the point 1 and 3. I'm not sure what that means there, but this is it. The line joining the two endpoints of the graph, there should be a point somewhere whose tangent line has the same slope. X equals 2 did not work because it was in the open interval. Exactly that. As Connor suggests, 2 is not in the interval, in the open interval minus 2 to 2. Is there an example where there are infinitely many c's where the derivative is 0 but the function is not constant? Sure. Sign next. Right. The derivative is 0 infinitely many places. So let's finish this up here, right? This function is continuous everywhere it's defined. So as long as you stay away from 0, you're good to go. And here we're far away from 0, so that's good. So this function is continuous on the interval 1 to 3. It's also differentiable there. You know what its derivative is. It's differentiable on the open interval. So the hypotheses of the mean value theorem are satisfied. The derivative, negative 1 over x squared, and the mean value theorem says that the slope of the line joining the endpoints is equal to f prime of c for some c in the open interval 1 to 3. So what is this? F of 3 is 1 over 3, minus f of 1, which is 1, over 2. This should be equal to minus 1 over c squared. This is minus 2/3 over 2, so this whole thing is minus 1/3. Minus 1/3 is equal to minus 1 over c squared. So you see that c is plus or minus root 3 as predicted by critique. And only one of these, again, is in the open interval. Only the positive 1 over root 3 is in the open interval 1 to 3. As Sophia suggests, we would not be able to apply Rolle's or the mean value theorem if it wasn't differentiable in the whole interval. Exactly. Which is why the question is asking us to verify that the function satisfies the hypotheses. You cannot apply it if the hypotheses are not satisfied. And Sophia is asking, what if it was differentiable everywhere except at one point? Could we not work around it? And the answer is no. You could not work around. And one example of that is number 22, which I was going to do, and then I wasn't going to do it. Why don't we do it? Let f of x be 2 minus 2x minus 1 in absolute value. Show there does not exist a c such that f of 3 minus f of 0 is equal to f prime of c. Well, let's say this. So as Gabrielle suggests, the point C is a point where the slope of the tangent line is equal to the slope of the line joining the endpoints. That's exactly it. Is there a special relation between intermediate value theorem and mean value theorem? There is not. There is not. I don't know what section that is, but it's mean value theorem section. Still in the mean value theorem. Right, so look at this. Right, you see that this business here is the conclusion of the mean value theorem. And yet, in the mean value theorem, it says that there does exist a C such that this is true. Whereas here, we want to show that there does not exist a C, right? So is this contradicting the mean value theorem? Hopefully it is not, because we proved the mean value theorem. So you know it's true. So this better not be in contradiction. And what goes wrong here? Well, I think you know what happens, right? This function, so first of all, let's rewrite the function. Absolute value of x, you know to be x if x is bigger than 0, and negative x for x less than 0. So absolute value of 2x minus 1 is 2x minus 1 if 2x minus 1 is bigger than 0, and negative of that and this is equivalent to saying x is bigger than 1/2, and this is x less than 1/2. And as Connor predicted, and others as well, you know that it's not going to be differentiable at 1/2. Right? I mean, you've seen this before. You know there's something fishy with the absolute value. You have this corner happening. So your function, which is 2 minus absolute value of 2x minus 1, what is that going to be? It's going to be 2 minus 2x minus 1 for x bigger than 1/2. And it's going to be 2 minus negative, or 2 plus, for x less than 1/2. Or in other words, let's rewrite this as 2x plus 1 for x less than 1/2. And 1 minus 2x, no, 3. 3 minus 2x for x bigger than or equal to 1/2. Right, and you can easily see that this is, so first of all, these two pieces are polynomials. So continuous, the only place we need to worry about continuity is at 1/2. And as x goes to 1/2, this part goes to 2. And this part also goes to 2. So continuous at 1/2 as well. So this function is continuous on the closed and bounded interval 0 to 3. And what is the derivative? The derivative. Well, the derivative of this part is easily seen to be 2. The derivative of this part is easily seen to be minus 2. What about the derivative at 1/2? Well, to find the derivative at 1/2, we need to use the limit definition. And you know what's going to happen. F prime of 1/2 is the limit, whatever you want to do. As x goes to 1/2, say, of f of x minus f of 1/2. And now this is going to depend on whether x is bigger than 1/2 or x is less than 1/2. So let's do the less than 1/2 first. F of 1. So for values less than 1/2, this is the function we're using. So this is 2x plus 1. F of 1/2 is 2. And so this is 2x minus 1. And if you factor out a 2, you get x minus 1/2 over x minus 1/2, whose limit is 2. Similarly, can I for values bigger than 1/2, this is what we're using. 3 minus 2x. F of 1/2 is still 2 over x minus 1/2, and this is easily seen, right? Same thing. You're going to get it minus 2x plus 1. You'll factor out a minus 2. Everything will cancel. Blah, blah, blah. This would be a good final exam question, absolutely. No, you have to use the limit definition. You have to. I mean, I guess you could draw, but the limit definition is the way to go. So limit from the left is 2, limit from the right is minus 2, so this does not exist. So you see the derivative is either 2 or negative 2. And f of 3 minus f of 0 over 3 minus 0, what is that? F of 3 is minus 3. F of 0 is 3. No, f of 0 is 1. So this is minus 4 over 3. And this should be equal to f prime of c for some value of c. But the derivative is always 2 or negative 2. Never negative 4 over 3. So as critique suggests, the limit, this limit does not exist, and that limit was the derivative. the derivative does not exist. So you see, there is no point satisfying the conclusion of the mean value theorem. This does not mean this is a counterexample to the mean value theorem. Rather, that one of the hypotheses of the mean value theorem did not hold. Your function was not differentiable on the whole open interval. Convinced? So what's the final answer, right? The final answer was asking us to show there does not exist a C such that f prime of C was this. But this is negative 4 over 3. And the derivative is either 2 or negative 2. So it's never equal to negative 4 over 3. Ren, I'm not sure what you're asking there. Paul is confused as to why f prime of 2, we need to show f prime of 2 does not exist. Well, we're looking for the derivative of the function, this piecewise defined function. The derivative for values less than 1/2 is easy to do, it's just 2. The derivative for values bigger than 1/2 is easy, it's just negative 2. The question arises, what about at 1/2? What is the derivative at 1/2? That's the question. And as Bree suggests, if the function isn't differentiable throughout the whole interval, the mean value theorem does not hold. Well, I mean, the conclusion might still hold, but not by the mean value theorem. Well, you cannot just use the mean value theorem because you don't know. You don't know. And the negative 4 over 3 here is f of 3 minus f of 0 over 3 minus 0. All right, people, we have to move on. Consider this. Show that sine x is less than x for all x in the interval 0 to 2 pi. Now that would be a nice final exam question. And you see, it's not clear that this is a mean value theorem question. Right? But it is. So now that you know it's a mean value theorem question, what are you going to do? let f of x be sine x. Right, and Eddie is reformulating the question. This is equivalent to saying sine x over x is less than 1. Very good, but now you still have to prove that. Right, so let's define Connor, I don't know that does it though. Just because the slope of the tangent line is greater for one function than the other doesn't immediately mean that one is greater than the other. Let f of x be sine x and apply the mean value theorem to the interval 0b. Could we not use absolute maximum? Maybe. Maybe there's a way to use absolute maximum. I'll let you work it out here. Interesting. It's an interesting, Sarah's suggesting an interesting approach. Right, so let's define f of x to be sine x and apply the mean value theorem to the interval 0b. First of all, sine x, very well behaved. Continuous, differentiable, blah, blah, blah. F is continuous on the closed interval 0b. And differentiable on the open interval 0b. So how could you work out on the exam that this is a mean value theorem question? It's a valid question, right? Experience is how you're going to work that out. You'll have done so many of these questions that you'll know. So if we apply the mean value theorem, f of b minus f of 0 over b minus 0 should be the derivative at c for some c in the open interval 0b. Why 0b? Let's just go with it, see what happens. And what does happen? Left-hand side is what? F of b is sine b. F of 0, sine of 0, you know to be 0, over b minus 0. And that is the derivative of sine is cosine of c. Now, what did you know about cosine? Did you just replace 2 pi with b? Well, I mean, the idea is that we want to prove for any value between 0 and 2 pi. So I'm essentially calling it b and see what happens. Notice I did not even make the distinction that b was less than or equal to 2 pi. In fact, we will prove it. We will prove this not only on the interval 0 to 2 pi, but 0 to anything. And as Eddie suggests, you know that cosine of c is less than or equal to 1. Well, that's actually where... Good. Where did I get cosine of c? The right-hand side is f prime of c. Derivative of sine is cos. Right? So here we have the less than or equal to. Notice we want a strict inequality. So that's where if we let b be strictly bigger than 0 and less than 2 pi, the only place cosine is 1 is at 0 and 2 pi. So cosine of c, if c is in the interval 0b, c cannot be 0 and cannot be 2 pi, and so we get a strict inequality. And then you're done. So sine b is less than b for any b between 0 and 2 pi. Or sine x is less than x for x between 0 and 2 pi. Isn't that nice? Exactly. Cosine is always between -1 and 1. How did you establish that sine b is more than 0? We did not. We did not, and it's not an issue. Well, sine b over b is cosine of c. So we don't know that sine b over b is less than 1. But we do know that cosine c is less than 1. And since the two are equal, the other one has to be less than 1 as well. How are we doing? Let's try another one. How do we get rid of cosine c? Cosine c is less than 1. You know how cosine behaves. How is cosine c less than 1? Well, I mean, what do you know about cosine? Why does sine b or b less than 1 make sine b less than b? Henry, you tell me. Look, I mean, exactly. You know, we've been using that forever, right? You're correct, Con. Cosine of 0 is 1. And Henry has answered his own question. You know exactly right. So, I mean, we were saying cosine oscillates between -1 and 1. So cosine x is less than or equal to 1 and bigger than or equal to -1. So this is the inequality we're using. The only issue is we want to make sure it's not equal to 1. So where is cosine equal to 1? Right? I mean, we want a strict inequality. So let's make sure it's not equal to 1. When is it equal to 1? Well, it's equal to 1 at 0, and then at 2 pi, and then at 4 pi, and so on and so on. So if I'm restricting my attention to the open interval, not including 0 and not including 2 pi, then it's never equal to 1. If I'm restricting my attention to the open interval, it's never equal to 1. Strictly less than 1. In this case, why don't we make it be bigger than -1? Well, I mean, you could have included some stuff. In other words, take negative values, but then when you try to bring the b over, the inequality is going to reverse because you're multiplying by a negative. So we're going to have issues there. Is that why sine x is just less than x? It's exactly why. We've proven it. Exactly that. That's our conclusion. Precisely that. Oops. One way. Rubbing that off there. Unique real solution. Right? I mean, it's a very nice, slick proof that sine x is less than x, which we like to use, right, in the limit idea there. All right. Show that this has a unique real solution. And, you know, people have been asking, what's the relationship between the intermediate value theorem and the mean value theorem? And I keep saying there is none. And then boom, here it is. Here's the relationship. Exactly, Caesar, right? So let f of x be x cubed plus e to the x. We're going to use the intermediate value theorem to show there's at least one real root, right? This is continuous. This is continuous on the whole real line. F of 0 is easily seen to be 1. F of -1 is -1 plus 1 over e. And this is a number between 1/2 and 1/3. So this is going to be less than, if I make this as large as it can, right, so f of 1 is less than -1/2. So by the intermediate value theorem, since 0 is between -1/2 and 1, there exists Gabrielle's not sure where the 1/2 came from. Well, I mean, it comes from the fact that we don't have a calculator. Right? I mean, here we're looking at 1/e, which is 1/2.71 something, something, something. And if you make the denominator smaller, you make the whole fraction larger. So this is less than 1/2, but bigger than 1/3. Right? If we had a calculator, you could work everything out, but on an exam, you don't have a calculator, so you need to be able to approximate these things easily, and it's not a big deal here, right? So by the intermediate value theorem, there exists an element A in the interval -1 to 0 such that f of A is 0. Is the negative fx just a chosen value? Well, I mean, you know what you're trying to do, right? You're trying to show that f of x is equal to 0. So if you can show that it's continuous and it's bigger than 0 somewhere, less than 0 somewhere, then by the intermediate value theorem, it has to be 0 somewhere in between those two values. And that's exactly what we've done. It's bigger than 0 at 0. It's less than 0 at -1, right? So a graph of this, at -1, you've got some negative value. At 0, you're at 1. And it's continuous, so you can graph it without lifting the pencil from the paper. It has to cross the x-axis somewhere. There was no specific interval, right? We came up with this just by looking. Nothing was given except this question. So it's up to you to do whatever you want to do. Intermediate value theorem gives us the existence of at least one root. But now the question is asking us to show there's only one. We've shown there's at least one. There could be more. Then we need to show that there is no c such that the derivative is 0. Very nice. Very nice, Connor. Right? Suppose there is a second root. Eddie has suggested an alternate approach. Could we not show that it's always increasing so that when it does cross the x-axis, it never comes back down to cross it again? And that would be acceptable as well. So two approaches. Either show it's always increasing and argue that once you cross it, you don't come back down. Or let's do it in a mean value theorem sort of way, or perhaps Rolle's theorem. Suppose there's a second root. Suppose there is a second root, x equals b, where f of b is 0. So you see now you're in a Rolle's theorem kind of situation. F of a and f of b are equal. So by Rolle's theorem, applying Rolle's theorem to the interval AB or BA, whichever one is or BA, if B is less than A, because I mean, we don't know how A and B are related. One has to be bigger than the other. They're not equal. So one has to be bigger than the other. If B is the bigger one, you're going to apply Rolle's theorem to this. If A is the bigger one, you're going to apply Rolle's theorem to this. In either case, f of A and f of B are equal. So it doesn't matter. And by Rolle's theorem, there exists a C between A and B where the derivative is 0. But what is the derivative? The derivative is 3x squared plus e to the x. 3x squared is bigger than or equal to 0, and e to the x is strictly bigger than 0. The exponential is never 0. So f prime of x is always strictly bigger than 0. So f prime of c is never 0. Contradiction. Contradicting the conclusion of Rolle's theorem, where the derivative had to be 0 somewhere. So an assumption we made must have been false. And the only assumption we made was that there's a second root. So you cannot have a second root, and consequently we knew there was at least one. There cannot be two. So there must be only one. How we do it? Questions? Anyone? A good place to end then? All right, practice this. Maybe we'll do one more example on Friday, and we'll pick it up from there. Okay, and I will see you on Friday.